Okay. Well.
Okay. Can I get started?
Yes, go ahead.
All right. Thank you, folks, for making it over here. Today, I'm going to be talking about TinyML or tiny machine learning. And one of my cute little tags around it is saying that the future of machine learning is tiny and bright. So today, I really have kind of like three primary things that I want to get across. It's first and foremost, it is introducing the concept of TinyML. And then I'm going to talk about three fundamental primitives or pillars in my head that we need to kind of establish around sort of what this field is and how we can move this field forward in terms of understanding some of the challenges around supporting the ecosystem around ML hardware, specifically in the embedded system kind of context. There are some really unique challenges in the space that are quite different from the rest of the bigger ecosystem. So I'll talk a little bit about that. Then I'll talk about how do you get the industry together in order to kind of establish some sort of standardized principles in comparing systems, which is extremely important if you really want to make headway in sort of like nascent field like this. That's the second point around standardization. The third point is going to be around acceleration. How do you accelerate the field in terms of adoption and having people actually develop and do interesting things? And in the machine learning context, that ends up being around either building models or around data. Building models is really boring, so I'm going to be talking about building data. Right? How do you build data sets? How do you automate it, and so forth? So to back up and talk about it, I'm saying I'm going to introduce what TinyML is as a context. Then I'm going to talk about three pillars, which is generalization, then standardization, and then acceleration. These three things. And at the end of the talk, I'll come back and I'll tell you about the artifacts that I'm going to leave you with, so you can kind of know where to go next. And this talk is not intended to be a research talk, so I'm not going to be going bonkers on data and so forth. Nonetheless, if there are questions that come up, please feel free to interrupt me. And I think the best way would probably just be like, maybe at least on my end, if you just do a reaction or raise your hand or something like that, that'll be helpful through Zoom. Awesome. So with that said, let's get started. I don't like making any assumptions, so I'll kind of start off with the very, very basics. So obviously, we're going to be talking about machine learning. I just want to establish the terminology so we'll be using. Machine learning is a subfield of artificial intelligence where what we're primarily focused on is trying to understand patterns and data, right? And within that kind of context, we'll specifically be talking about deep learning in the context of tiny machine learning, right? So I'm going to use machine learning in the title, but really we'll be focusing on deep learning. And later on, I'll talk a little bit about some of the differences and tiebacks, because TinyML actually dabbles both in terms of deep learning and machine learning. Deep learning is the kind of hype and buzz that most people kind of heard about, using neural networks and having lots of data and trying to infer interesting research patterns that are encoded inside the data and being able to extract that and then build interesting applications. Now, typically when we talk about machine learning, there are lots of applications, right? Machine learning is really like, as much as there is excitement around it, it's actually really, it's something that we already take for granted, because when you take a picture, you're running machine learning, right? When you're talking to machines like Alexa, Google, like, when you say, hey, Siri, and so forth, you're basically interacting with machine learning. And of course, if you're on social media, which I am not very active on, those things are practically run with machine learning. And there's some really interesting pros and cons about it. All right. So because I'll be using some examples and so forth, I want to just kind of define some of the classical, textbook style examples, because I'll just use the words later on pretty heavily. So in the most obvious kind of, machine learning task is really just being able to do classification, right? Looking at a picture and then being able to say, classify, is it a cat or a dog, right? Then you have detection. Detection is a little bit different from classification in the sense that when you look at an image, you're not simply going to say, hey, there are some oranges in here. You're not going to say they're just oranges. You're actually precisely going to identify exactly where in the image is the actual orange sitting, right? Detection can actually be multiple classes. You can have like instance sort of detection, which is what I'm showing here, where you can precisely identify multiple of them individually. Or you might just, put a giant blob around this whole thing and say orange, right? But the point of detection is to be able to extract precisely where in the corpus of pixels that you're looking at is the information that you care about, which becomes very important in autonomous driving or shopping or anything. Because if I show you a picture, you want to be able to detect exactly where a handbag is or where those really cool shoes are. Segmentation is precisely identifying in a given picture, right? This is happening in real time for autonomous vehicles, where you're trying to say which parts of the image are they pixely correlated, right? So for example, there are autonomous vehicles, there are cars here, the cars are all in a single color. Then the side road is kind of like, in this purple color, saying that that's off-road. People are in a particular color. So segmentation is all about precisely identifying where in the pixels, which pixels are all effectively correlated together, as compared to detection, which kind of just gives you a bounding box effectively. This sort of precise information is obviously extremely important in autonomous vehicle use cases. Of course, there's machine translation. For example, you probably have used machine translation where you've come across an interesting web page that looks really interesting, but it happens to be in some foreign language. And on the fly, you can Google, you can click an icon on your Chrome browser or something, and then it immediately translates it into a localized language that you understand, right? Then, of course, one of the most popular machine learning applications that we all take for granted when we watch Netflix or anything on YouTube and so forth are really recommendation systems. Recommendation systems are perhaps the most important class of machine learning applications that are actually deployed, because this is really what makes money for the big organizations, right? In fact, just an interesting tidbit, Facebook has said that over 80% of their cycles in their fleet are really spent on recommendation, which I suppose is not that surprising because, well, Facebook, you got to know what images you're going to like or what's the next most interesting thing that you actually want to see. But the key thing that is kind of fueling all of this, machine learning intelligence and all these applications that we take for granted are really the big data centers that we have in the back end, right? These are somewhere up in some remote places, and they're burning a lot of power and consuming a lot of electricity in order to be able to provide those applications. Now, these are so big typically that you're actually building them, close to dams, for instance, and they look like giant football fields, right? So the energy consumption is sort of an extremely critical problem. And a lot of people are really worrying about this, is how do you have green AI? Because anytime we use any kind of application service, right now, even if you touch Alexa and you say, hey, Alexa, I actually know the team that actually deploys that stuff. When you say that, it actually ends up in the cloud, right? So it goes all the way up into these data centers. So then you got to think about the infrastructure, the networking infrastructure, the compute infrastructure, and all that we're going to have in order to be able to power these services. In fact, interestingly, Google has been building custom hardware that I'll talk about it a bit more. One of the reasons that companies are now building custom hardware for these applications is because, at least in Google, I know they realized that that if everyone basically used, I believe, Google Assistant for I think something like as short as maybe a minute a day throughout the whole day, throughout the 24 hours, they'd effectively have to double, triple their data center fleet within about 5 years, which is physically impossible for them to achieve, right? So that was one of the big reasons that big corporations have started looking at how can they actually try and enable intelligence much more efficiently. To that point, one of the key things that's been happening in the domain is that there's been a massive amount of computational demand for these applications, right? What I'm showing you here is this plot that comes from OpenAI. What this plot is showing is between 2012, since I would say effectively the birth, from a practical standpoint for machine learning, from the birth of having AlexNet, which was the key network that kind of helped kickstart this whole revolution, to somewhere about a year ago or so with AlphaGo Zero, for instance, there's been a 300,000x increase in terms of computational demand for actually training these networks that we're, and by and large, starting to take for granted, right? And that's a very short time span. If you kind of think about it, this is, one could argue this is just about 5 to 6 years effectively in the grand scheme of things. And this is an astounding increase or demand in the computational horsepower. Now, typically, when you're looking at computing systems and you're talking about Intel, AMD, and these kinds of companies and what their ability to actually improve performance, they have been historically improving performance over this same time period. If you look at it, what they would have given us is only a 12x increase in computational horsepower. Literally, if we just sat back and just relied on Moore's law, we would have only gotten a 12x increase over this time period. But the contrast is really there's a significant thirst for just raw computing horsepower, right? Now, there are multiple ways you can overcome this 12x, which is by parallelization, which is by building custom hardware and so forth. And doing all of that is ultimately what kind of has led us to be able to, build these amazing neural network models that have been able to play and beat some of the world champions in AlphaGo and so forth. So the key point of this slide is that, machine learning models are extremely computationally heavy, right? One of the really crazy things, as much as I'm saying about this stuff, right, is like if you compare this to a historic trend. So the plot that I just showed you somewhere in here, right, this little regime. If you kind of compare it to, machine learning having been around for such a long time, between 1960s to 2010, like this sort of pace at which we're going is really incredible to what has been traditionally known in the machine learning space. So the computing is basically, not going to slow down. Now, this is all about really, really big compute that we're talking about, right? And this is where I was alluding to the fact that given our thirst as consumers of this technology, what we're doing is we're building like really custom hardware, right? There's GPUs that we have gotten used to, which originally just used to deal with basic graphics, but we have since then evolved into doing general high performance computing, which have now started literally specializing in for machine learning tasks for all the different kinds of example applications that I mentioned earlier. Google was one of the first ones that, as a software company, actually started ending up building custom TPUs or tensor processing units. And their entire goal was primarily that, look, as I said earlier, like if everyone wants to use, say, Google Assistant just for like, a fraction of a day, right? Then they'd have to double, triple their fleet, which is both costly and it's just impossible to really do. So they started building custom processors that just did one task. They helped us run machine learning, all these machine learning models really efficiently, both in terms of training them, as well in terms of actually deploying them in the fleet so that you and I can actually enjoy the benefits. So custom hardware is really good. And these are all just, these are still silicon based, right? CMOS based. Things are getting so crazy right now. For example, this is a company that I actually helped, work with in Boston, which actually grew out of MIT. And my colleagues here have been actually building what they call as a photonics accelerator. A photonics accelerator is basically going to do all the math literally through phase shifts in light domain, right? So you go from electrical domain, which is it consumes a lot of power because you're switching these transistors on, you're switching these transistors off. So that consumes a lot of power. Even just kind of keeping them on ends up leaking power, right? So because the demand is so insanely high for these applications, right? People are now looking at, hey, what are some fundamentally new technologies that we can use that will allow us to, do all of this AI compute extremely efficiently with ultra low power, right? And so Light Matter is just one example of a company that is trying to do photonics. Like they try to do all the core computation of photonics, which is amazing. And the point I'm making here is that people are going bonkers about this stuff, right? There's so much excitement around this space. And this has always been about like building big systems up in the server side, right? So, however, there are some sort of trade-offs around just kind of doing everything on the server side, right? Anytime you want to do, you want to train a model, anytime you want to ask Alexa or Google or any kind of intelligent question, what ends up happening? Your voice ends up going all the way up to the cloud, right? And that's where all these requests are coming in. These billions and billions of requests are coming in, and then they have to do the inference right there in the fleet. Now that has got a lot of problems, and we're starting to get really concerned about the amount of power these systems are going to start consuming. Just as one example, this paper really kind of kickstarted a lot of discussion around this concern around how much energy are these AI models really consuming. This paper is a very short read. I encourage you to kind of take a look at it. It's a fun read, and it's also like thought-provoking. But the ultimate thing that they really come down to is kind of like looking at it from a climate sort of a perspective, right? Sustainable computing is extremely critical. We all care about things that are happening around us, around climate change and so forth. And computing is one of the key consumers of electricity. And so it has a huge amount of impact on climate if you're not careful about this. And especially the rate at which we're going nuts about this machine learning stuff is almost detrimental. And that's what this particular figure here is trying to capture, right? It talks about the amount of carbon footprint that things consume. So for example, this is in pounds of carbon dioxide, right? So if you take a flight basically from the West Coast to the East Coast, right? And vice versa, that's about 2,000 pounds of carbon dioxide that it creates. Now, and this is about a human life on average, right? About 11,000 something. American life, I don't know what's the difference here particularly. But if you look at a US car, well, that's 126,000 pounds of carbon dioxide. And if you look at this and from the perspective of training neural networks, the last row is what we really care about, right? Transformer network is one big type of a neural network that is used. And you can see the amount of carbon dioxide that they're saying it's gonna, it consumes, right? And this is basically for training the model. This is actually not really doing inference. Inference is when you actually hit the thing all the time, right? When you're constantly making Google searches or when you're asking anything on Facebook, that's the inference part, which is actually exercised trillions of times. This is just the training part, which is actually getting, how do you get this really smart neural network that can tell me, are there people on the road or is it actually cars on the road, right? In this particular case, it's all about natural language processing, and you can see it's a staggering amount. And there are lots of articles out there that say, like, in order to train this thing, it takes practically five cars entire lifetime, right? That's the amount of energy we're consuming. So there's some real big concerns around, hey, is building all these really, really big systems up in the cloud a really good thing for us to be doing just as a whole? So bigger is not always better is my fundamental point that I'm getting to. And we have sort of, because of this, right? Because of this and many other reasons, what we've started seeing is the shift from going from data center sort of computing over to more on, more towards the edge effectively, right? In some capacity, if you kind of look at it, our smartphones nowadays do a fair amount of machine learning. They don't necessarily, when you take a picture, for instance, it's not necessarily sent up to the data center in order to enhance it, right? Virtually, if you have any recent phone today, all of these phones are basically running machine learning models between the camera, the ISP, the image signal processor, and the display screen and the GPU. There's a big neural network that is basically doing super resolution and sort of enhancing the image in order to kind of make it look beautiful, right? So all of that has actually started increasingly moving towards the endpoint, which is closer to us. Lots of benefits about doing this, right? The most obvious one being that your data is just kind of sitting on your phone. It's not going up into the cloud because who knows what is actually happening with that, right? Yeah, we do things like, we can do things like image enhancement. Now, when you talk about, waking up these machines in order to communicate and say, hey, Google, like, show me my calendar, for instance, right? Or when you're doing question and answering, where there's some amount of information and you're asking, like, okay, for example, if you open up Wikipedia, you can ask a question like, okay, when was someone born, right? It'll immediately know where exactly the answer is and it'll kind of generate the answer for you. So these are things that are starting to increasingly happen where we're basically moving from large scale data centers over more towards the endpoint. Now, TinyML is kind of more at the spectrum of even pushing that even further, right? So this is already happening with, having assistants in your house, right? An assistant is basically in some capacity more pervasive than your smartphone. Your smartphone is with you, right? But an assistant is practically inside your house kind of thing. Like it knows a fair bit about the context. Now, as we kind of think about it, what we're effectively seeing is that more and more of all of that intelligence is going to end up in all of these devices that are all around us. And the big reason that the shift is happening, where we're moving a lot of this big machine learning, or fat machine learning, as I like to call it, over to this tiny machine learning, is really because of these 5 reasons. Bandwidth. Think about the fact that if you have like a lot of these devices, right? And I'll talk about some numbers later on, but if you have a large number of these devices, then the question becomes like, well, are all of these devices going to be pushing all the data up into the cloud so that you can do some sort of interesting inference on them? That bandwidth, the volume of data that these devices are going to be able to generate is staggering, that you would actually not be able to effectively deploy it. That's the real concern that people have. It's just having the raw computational horsepower in order to move the data from here through the network and up into the cloud. And then you got to push that information back in real time, right? So that corpus of data, that's the problem. Because a lot of these sensors are dealing with an incredible volume of data. If you kind of think about like when you're just brushing, right? So just kind of imagine like my toothbrush is a smart toothbrush and actually makes recommendations on the fly as to when I'm brushing, if I'm brushing well or not. I had to get it because when it said AI, I was like, I got to try this toothbrush. But the interesting point is that like that sensing is constantly looking at a huge volume of data. So if I try to transmit that data, I'm going to be in a big problem, especially when I consider all the devices. The second thing is around reliability. Let's say you have a car, right? Just take a regular car, right? And let's say you're dealing with a braking system, right? Now, a lot of the interesting applications of around embedding machine learning at the endpoint is all about like, safety and so forth. So in a car, for instance, it might be about like having a brake system that is kind of like, I don't know, listening to the sound of the wheel, or it's sort of monitoring the spins or something like that. Now, imagine the fact that like if one of these sensors, if you want to send this data out, right? Like sometimes networks go out, right? Are you sure that your data is actually going to go and come back in the time that you need? So this notion of reliability is becoming a pretty important concern around machine learning. It's just how reliable is this deployment of this machine learning on this device? Then, of course, there's the notion of latency. Like in that braking system, for instance, I might need to have a very tight loop. I can't just send this off and then, I have some big data, and then tomorrow morning, the car tells me that, oh, by the way, there's something wrong with the wheel, and the wheel's about to pop off in the next 5 minutes. Well, you probably already popped off, and then you probably died, right? So latency is actually quite critical. If you talk about AV, latency and reliability are extremely critical. And then there's privacy. Do you let's say you have a smartwatch, you got, there's a lot of health data on it, right? The Apple Watch, for instance, collects an incredible amount of volume of data, and a lot of other health gadgets are sensing all your data. One of the big concerns that we have is do we really want to offload all this data up into the cloud? There are things like fully homomorphic encryption and things like that that are down the path of maybe coming where our data can be sent in an encrypted way. You can do machine learning on it in an encrypted way so that people the consumer, the corporations would actually not know what the data is, but they're operating on the data. Well, those kinds of things still there, but they're so far out, right? So the concern right now is how do we get our data and have all this intelligence on this raw data and convert that into information, but keep it private for ourselves. So privacy is sort of a key element that's emerging, especially in health applications. And of course, there's always, no matter which application domain you're kind of talking about, right? All of them, or safety critical applications, or health applications, or any other application, the ultimate concern you're going to have is really energy. Right? You need to have, if you're going to have machine learning, which is a computationally intensive thing, compute, though relatively, is often much more cheaper than actually dealing with communication. Right? If you look at any kind of device, typically over 50% of the budget is typically allocated for communication, because transmitting data is crazily costly compared to just kind of computing things. So any kind of transmission is going to be extremely energy inefficient, right? So, and it's, most of these devices are operating on battery power, right? So your watch, your toothbrush, or something are operating on battery power. So if you kind of think about these kinds of devices, and if you want machine learning to be pervasive, you really have to solve the energy problem. And if you want to solve it, well, first, don't do dumb decisions, which is don't communicate all the data out. Try and keep the data as much local as possible, so that way you can spend the energy more efficiently on compute. So there are many reasons like this that basically you can boil them down to these 5 sort of principles as to what we really care about around why increasingly we're seeing machine learning wanting to be deployed at the endpoint on the device for real-time connectivity. Now, to summarize all of this stuff, what I'm trying to say is that the first slide effectively I showed you is saying hey, machine learning and deep learning are all about extracting patterns. And if you want to get those patterns, you basically have to have lots of data. Well, you know what? Those examples that I showed you earlier, we're all excited about it. Yes, it drives an insane amount of activity around our planet. But the truth is there is so much more that is untapped right now. So, if you kind of look at IoT devices, which are basically those kinds of, everyday devices that I kind of mentioned, you can have an insane volume of data that they're producing. And you can sum it up and say that less than 1% of all of this unstructured data is actually used. Structured data is basically things that are in tables and nicely formatted and so forth. Unstructured data is where there's a lot of raw data that's not really curated effectively. That's unstructured data. And so, you can just see that if we're all excited about machine learning right now, I kid you not, in 10 years, we're probably going to see a world that you and I actually can't imagine if we're working in the space, because I think a lot of the creativity is going to come around with people who unlock the capabilities within tiny machine learning. So with that said, hopefully what you've gotten up until this point is that why we're increasingly seeing machine learning capabilities, which start off on the big side in the cloud and data center side, are increasingly moving down towards the endpoint, right? And as we go towards the endpoint, it might seem like we're going towards small devices, but it's true. But that's where, it's like an inverted pyramid, because the volume of devices that we're actually going to look at is insanely large. And talk about some of that right now. So let me first start off by defining TinyML, because I've been wishy-washy until now. So TinyML is all about, it's one of the fastest growing fields. And this is my personal sort of opinion around this, because fast is relative. It depends on what you're talking about. But in the context of embedded systems, it's hands down the fastest growing field of machine learning. It's really fascinating because it levels the playing field from multiple dimensions. It involves machine learning algorithms, but it's not about just taking a machine learning algorithm and then dropping it on some hardware. It's really about dropping it on embedded hardware. Now, we're in the embedded community, so I'm going to assume a lot of us have some flavor or some idea about the complexities of embedded hardware, where there's a lot of extreme specialization for energy efficiency and so forth. So you can't just take machine learning models and just assume they'll just run out of the box. I'll get much more into this later on. Then it's also dealing with embedded software, right? Which is also just as messy in a way, because embedded software, I mean, do we even have an OS on embedded hardware? Sometimes yes, sometimes no. But it's this confluence of machine learning algorithms coming in with some of the extreme constraints of embedded hardware along with the embedded software that really makes TinyML tick. But to solve this later on, I'll show you there's some challenges that we'll have to deal with. But nonetheless, this is this combination that's happening. And we're going to try and make this work. And I know all the engineers are always really smart. They will make it work, period. And the reason we're going after all of this is because we really want to do sensor analytics on device, right? Sensors, right? It might be a pressure sensor, a camera sensor, a microphone, like, temperature sensor. There are an insane volume of sensors out there. And what you really want to do is you want to take that high bound sort of data that's coming out of all these sensors. For each one, there's some specialty, right? And then you want to analyze that data in real time on that device. Now, the key challenge for us is really going to be how we unlock the low power consumption. But once we're convinced of the use case, it always happens. We'll engineer systems to meet the requirements. And hopefully, once we do that, we'll enable always on machine learning. And these devices will be able to run on battery power. Forget the whole notion of having something tethered to the wall. I want to be practical here and kind of help, especially with students, you might not know this. A very simple use case. Let's say, for example, I want to build a small little widget that detects whether there's a person or not in the room. A very common use case of this is conserve energy, right? Turn off the lights if nobody's in the room. Okay, so now let's say I say here, go ahead and actually give me a deployment in a consumer building, right? In some sort of corporate building. What does that really mean, right? Your first glance is going to be thinking about, okay, what's the technology? Okay, fine, the technology I'll give you in a black box, which is there's a machine learning model or some code that's able to see from a camera input whether there's a person or not. So that's done. The question is, how do you deploy this? Now, if you want to do this intelligently, what you're going to have to do is first, you have this device. Well, this device is going to have, it's obviously running computer vision and so forth, right? So it's going to be needing a lot of power, which means now you have to run a cable, right? You got to keep it powered up. Okay, if you want to install something seriously in any kind of corporate building, this means that now you have to get an electrician to actually do the work, right? Now this means if you want to get the electrician's only going to be dealing with actually running the wire. But then you have to get permits because typically most places, the building's not owned, but people own buildings and they lease them out. So this means now you have to get permits, right? Now, typically, in order to make some good use of all of this, how well the whole system is working, let's say you put these devices in multiple rooms, then all of these are going to have to get connected up into some kind of server. Great, now you're going to run an Ethernet cable or connect it over Wi-Fi in some capacity. And if you kind of think about the amount of time it's going to take in order to deploy this very simple application, right? Just, turn the lights on or turn the lights off, right? You get very bogged down. Like there's all this intelligence capability you have, but in practicality, realizing that is slow because of all the mechanics that you have to get. Now, instead of that particular device, think of another device I give you, which has got that exact same black box of being able to detect a person and the ability to turn a light on and off. But all you got to do is take this device and just literally peel the sticker off the back and just stick it on a wall. Right? And in terms of connectivity, just assume it's a Wi-Fi based connectivity or some sort of low power connectivity like LoRaWAN or something. Those two are extremely different scenarios in terms of enabling the intelligence at an endpoint. Right? And that's where the whole notion around battery powered exchange comes in really into practice. When you talk to people in the field, when they're trying to deploy any kind of machine learning intelligence, they run into a lot of obstacles that are just not about the technology. It's actually about the mechanisms by which you have to deploy this, right? So in this other system example that I gave you, which is completely battery powered, assume you can run this device for 5 years, right? You just peel the sticker off, you stick it someplace, and then you just connect to it and then connect to it over Wi-Fi, and then you get. That is a radically different way. And that's one of the big practical reasons that actually people are really excited about, embedded machine learning or tiny machine learning, being able to deploy this, because it enables us, if we can get the low power down, then we can enable a lot of different use cases and actually generate a lot of really quick value. So what's the most common kind of example or use case that you deal with is like something like this, right? So for example, you know, when you say, okay, Google, well, that is a deployment. My machines usually wake up. Sorry. But yeah, one example is effectively, okay, Google, right? So machines wake up and then, sorry, 1 second. Okay. This is a very common example of where you're actually already interfacing with TinyML, because usually the keyword, you know, okay, Google is actually the thing that is actually really efficient. Your whole phone is actually not active. Your whole SoC is not actually active. It's only an AOC block, which is an always on computing block that's made up of ultra low power DSPs or MCUs that are actually continuously listening for the keyword. And then if it detects it and it's confident, then it actually wakes up the main processor on the phone, which consumes a lot more power, but then it does much more complicated things like lighten up the display and all this stuff. Another example is, you know, when you say, hey, Siri in your watch, right? Exact same thing is going on, right? Or when you say, hey, Alexa. These are extremely common examples and use cases that we see. Now, more forward-looking applications that are on the horizon, we actually want to get that sort of intelligence, not just from speech, right? But any kind of camera application or sensing application is like, you know, having autonomous drones, for instance. You know, a lot of us see some wickedly cool demos around drones and think all of this stuff is actually happening on board. 99.9% of the time, the compute's actually happening on a workstation that we don't physically see, right? So just the raw commands, the flight control commands are the ones that actually end up on these devices. But increasingly what we're seeing at some of the best tools is like, there's compute that's actually coming on board. And it's all about, if you have embedded machine learning, then you can enable things like end-to-end control, which is like you go straight from pixels to control motions of the rotors, which enables us to kind of put intelligence directly on board. And it's extremely important to have that kind of command and control on board, because if you really think of search and rescue kind of applications, you're sending these devices into places that often don't have connectivity. So you're not going to be able to connect back to some kind of server and things like that, right? And again, communication is very power hungry, and these devices have very limited flight time. My lab actually works on these things, and they can usually fly only for about 20 minutes, and then they run out of power. The small ones that are extremely small, that literally fit on your palm, literally fly for only about 6 to 7 minutes, but they're awesome because they can do extreme navigation with agility and in extremely small spaces. So that's an example where TinyML is extremely powerful. There are many other examples, like, you know, other robotic systems are loaded with sensors in order to figure out what in the world is happening, because they have to physically perceive, and they perceive things through a lot of different sensors. Then autonomous, ARVR, one of the biggest things that's happening, right? So like, you know, Facebook recently announced that they've been working with Ray-Ban on things. They actually have some other crazy ideas that they're working on, where for a lot of the augmented reality, right, or mixed reality, all the processing really has to happen in real time on device. They can't really offload it. One of the reasons is because like these devices are so power strapped. For example, you know, your phone consumes about 3 to 4 watts. Now, our phones get hot, right? Now, imagine trying to put a phone strapped right next to your head. You can just think like that doesn't conceptually work, because these glasses literally have to be as thin as the ones that I'm wearing, right? So the power budget ends up being like something like around 300 milliwatts, and they often have to do a lot of sensing because you're constantly moving. And if the images don't keep up with you, then you get very nauseous. So there's some serious practical applications, and these devices are typically loaded with lots of sensors where they have to infer the state and do a lot of processing on device. Of course, lots of biometric applications, and, you know, even the Neuralink and so forth are trying to increasingly use machine learning in order to sense and figure things out. What are the patterns in the data? So lots of really interesting applications, right? And again, it goes back to the fundamental point that, hey, we're barely scratching the surface. Now, if we can enable TinyML, like do all that machine learning processing on device, then we can enable a really, really rich set of applications across many different domains. And this is really why people are wickedly excited about the possibilities of what's going to come. So, assuming you kind of buy into all of what I've said, what I'd next like to do is to kind of start digging into how do we democratize this technology. What I mean by that is, what are the fundamental things that we're actually going to have to technically do in order to be able to actually enable this field? That there are example solutions here and there, but if you really want this to happen at scale, we're going to have to systematically think about the challenges, understand the challenges, and then go about solving them. So that's what I'm going to touch on for the rest part of the talk. So far we covered one thing, which is why is machine learning moving from big data centers and so forth over to the endpoint, where embedded systems are really sort of like going to be the, you know, the focus area. And then I talked a little bit about some of the interesting applications that we're potentially going to unlock in the future. And now what I'm going to do in the third set is, we just got 3 components, is really talk about generalization. How do we deal with the extreme heterogeneity of embedded systems? I'll talk about what I mean by heterogeneity, but these devices are very, very different from one another, right? So then you have to somehow understand what it means to deploy machine learning at scale, right? And then I'll talk about standardization. How do we establish some sort of guided best practices in the industry in order to get the industry to actually accelerate itself? This goes around benchmarking and performance evaluations and so forth. And the third stage is really going to be around accelerating things. Accelerating machine learning is not so much about like, how do I get these systems to run machine learning? It's not about getting the industry to kind of align and be focused. It's really about how do you empower the end users to kind of come up with interesting applications and use cases. And that, to me, fundamentally falls in the realm of actually data. If you can build data sets, right? What's the ImageNet of TinyML? There's nothing. It doesn't exist. It just does not exist, period. So how do you bootstrap this ecosystem? So I want to talk a little bit about data sets, and I'll give you a point example of something we have done. It's not just me, it's a big industry kind of effort, where we're trying to automate the creation of data sets for domains like TinyML so that we can enable interesting application use cases. And I'll talk about this in the context of speech. These 3 things in my head are somewhat like pillars. I'm not saying this is the only thing, the only 3 domains. Other really sharp people will come up with more of an ontology or a taxonomy around this space, but this is my first cut in trying to think of how to explain things to you. So let's talk about embedded systems at large, right? When you look at embedded systems, they're really small, they're really dinky, right? Like, just gonna put things physically for all of us, just to get, I've got a bunch of different embedded systems because I'm a geek. Like this one, right? So this one is, for example, Arduino. It's basically a Raspberry kind of a device that can actually run machine learning on device, right? And these devices obviously are very, very small. The interesting thing about them is that these devices come in many different form factors or many different capabilities. There are lots of different people who build these small little devices. These devices are just like, you know, maybe like you can get devices in the order of like less than $10. Like even for $5, you can get a small little embedded chip, which is why it's so awesomely exciting, because it's like the cost, it's like Moore's law, right? Like at some point when the cost kind of gets low enough and you have the volume, the movement just explodes. And that's effectively what's really going on in the ecosystem right now. So lots of different devices. These are just 4 random examples I picked, but there are many embedded systems out there. One of the cool things is that, like, if you actually look at these systems, these are actually development boards. In reality, the processors that are on them are already everywhere, right? So if you kind of look at like how many microcontrollers, MCUs, microcontroller units are out there today, that's roughly around 250 billion. It's a staggering amount, right, of compute that is out there. Just to kind of put this compute in the perspective of the rest of the ecosystem that I was talking about, the data centers and so forth. In the data center side, you might just have like about only 10 million servers. I've done some math a while back. I'd say like maybe about a year or 2 years ago. I kind of looked at shareholder reportings and so forth, and I back calculated it. And it came to about 10 million servers at that point. Maybe they're 20 million servers, big deal, nothing. At the end of the day, like that number is insignificant compared to the amount of these small little compute engines that we already have everywhere. In fact, I think just this year, ARM is probably shipping something like 30 million or something like that, some staggering number of microcontrollers each year. So the point of this slide is that they're pervasive, right? And that is wickedly awesome, because it's not like we have to build this custom hardware and then shove it out into the real world. They're already out there. So imagine if we can enable the intelligence on them, then that's when you really start the wildfire. Now, yes, these devices are out there, but I want to kind of give you a, I want to set the constraints on these devices, right? So just to kind of get into the right space. So I'll just kind of, again, randomly pick these few devices. They're just different makes of embedded systems. As you can see, like the different microcontrollers, I happen to just pick 32-bit versions here, but there are 8-bit versions, 16-bit versions, 32-bit versions. So they come in a rich variety of ISAs. That makes me realize that I should probably update these into this variance. Never mind. And if you look at the performance of these devices, they vary quite dramatically, right? So, I mean, you're looking at something that's like 64 megahertz here. This is, pretty weak. But there also, there are embedded systems that go up, right? This example, HiMax is going up to 400 megahertz, but still, these are relatively low performance capabilities compared to the systems like that you and I are on right now, like my laptop or your laptop or desktop, for instance, right? So remember that the clock speeds and so forth, the performance is very small. That's one thing. And the second thing is that, like, when we're talking about memory, you can look at the memory down here, right? So if you look at the SRAM we have, right? So it's in the order of like either megabytes, which is, but I kid you not that this is an extremely large device, 2 megabytes of RAM, right? Or you might have something like 256 kilobytes. So somewhere between 256 to 512 kilobytes is kind of like the mid to, very good mid-range devices, right? So this is very, very typical. These three configurations we're looking at are very typical kind of configurations for that microcontroller unit that I'm talking about. So the point that I'm making with the clocks and the memory here is that they have computational capability, but it's not at the same level as what we take for granted. On the memory side, this is a tiny fraction of memory capacity, right? So this has implications in terms of the network characteristics. That's what I'm trying to get to slowly. But never let these kinds of dinky, weak little numbers dismiss us, right? I often like to compare these numbers to what started the whole momentum around computing. If you remember the Apple I, Apple II, if I'm not mistaken, I believe that the Apple II, I think, had something like 16 megahertz clock, right? So slower than this. And I think it had maybe around a few kilobytes of SRAM, probably around 64 kilobytes of SRAM or something like that. And its storage, right, was around 80 megabytes. So what's the point I'm making? The point I'm making is that a lot of our computing revolution started out with these kinds of extremely weak and dinky little devices. And look at the world that we have all built. So I often like to tell students, if you're a student, really listen up. If you're a student, I kid you not, these could be the days of you all unlocking something remarkable in terms of technology or some kind of interesting application use case in your garage, right? If you just go back and look at the history of those old devices that everybody was geeking out about and had a really good time back in the 80s and so forth, it's almost like the same counterpoint. So there's an incredible amount of potential for these devices, given that especially today you can do machine learning on them. All right, in terms of sensing capability, they come with very different kind of sensing modalities, right? So here I have an accelerometer, a microphone, camera. Now the same kind of thing might also exist on the Arduino here, but this Arduino microphone and camera will have variations and differences, which are actually quite important because in TinyML, it's all about on-device sensor analytics. So that sensor is your really key input. Now, these sensors end up being very different, which means your networks end up having to get specialized for the input signals that are coming from here. And of course, from a connectivity standpoint, some devices don't have any connectivity. Others have something like Bluetooth. Others will have some sort of LoRaWAN. Point is that connectivity is something that is important to keep in mind because it's one thing to have intelligence on a device and be able to deploy it in the field. That sounds exciting. Now, what are you going to do if you can't get telemetry out of that thing, even though it's looking at all that sensor data? If you can't pull the data back, well, what kind of use is that going to be? You can't really build an enterprise or a corporate application out of that. So these are some real showstoppers and things that people have to think about. So far in the TinyML movement and the ecosystem, most people have been excited about the fact that, hey, I can actually get these neural networks to run on device with this sort of a performance capability with this amount of limited RAM. But they often forget about what really happens when you have to go into production. I'll try and close the loop right at the end of the talk around this because it's actually extremely important. Okay, so let's get a little technical and talk about some of the challenges that we have, right? So challenges in the embedded ecosystem comes from the fact or the way we have designed these embedded systems, right? Now, this can be in the context of hardware or it can be in the context of software. So I'll talk about the hardware first. First and foremost, the hardware ends up being extremely lean and mean. And those devices I was showing you, why is the SRAM so low? Why are the clocks so low? Well, remember, ultimately, you want these things to be running on battery power kind of thing, right? That's the ultimate thing. And those are development boards I showed you. When you actually really think about TinyML, it's going to have to run on ultra low power, which means you have to be efficient, right? So what ends up happening is, from a hardware standpoint, for instance, people end up specializing, engineers end up specializing these devices down for the specific use cases that they're actually trying to tackle, right? So often, if you look at a CPU, well, a CPU generally we think as, sort of a general sort of a platform, right? But in reality, the truth is that the CPU has extreme heterogeneity, right? And then you also have GPUs, DSPs, NPUs. So the point is, like, there are a lot of different embedded chip architectures in use in the wild today, far more than in any other computing domain. I'll kid you not, like, a lot of the data center folks and everybody is getting very excited about, heterogeneous architectures and so forth. I often like to tell them, well, maybe you should go look at embedded systems for a change, because you'll see the extreme heterogeneity that embedded engineers have designed in for efficiency. So in the context of embedded systems, you have like ARM class general purpose Cortex-M microcontrollers, which range from something like an M0 all the way to M33. And in these variations, you often have differences in instruction set architectures, because they're providing different functionality at different power and performance trade-offs. Then you have things like Tensilica DSPs, Qualcomm DSPs, Seba DSPs, Synopsys microcontrollers. Like, space is like crazily exciting in the sense that we have a lot of different processing engines. But the problem is that most of these chips have like really unique instruction sets that require their own compilers and software tool chains, right? Now, the reason, typically when we are thought about instruction set architectures and so forth, what are we taught? We're often taught to kind of think about, like, how does this instruction set architecture generalize or support general purpose computing really well? That's kind of what is typically taught in a classroom environment. But the reality is that, like, when you go for efficiency, you're going to start shaving off any little bit here and there, which means you're going to shave the ISA off. You don't want your decoder to be big inside the microarchitecture, right? Because that's going to consume power. So you're going to try and make it a very lean and mean ISA. Now, what this also means that implicitly, this is going to lead to a lot of fragmentation within the microarchitecture or at the ISA level, which means the code that I write for one version of, say, a microcontroller might not necessarily port over. And this is a serious problem in the industry today, right? So the instruction sets are often incompatible, even between different versions of the chip that's within the same family from the same manufacturer. It's crazy. This variety is basically to offer a nice little period of frontier trade-off of, what do you want, consumer? Like, what application are you trying to build? Because you can pick the efficiency with a very fine-grained lens. So bottom line is, the consequence is that the framework has to be radically portable. Like any kind of compilation you do or anything, ideally, if you want to be able to deal with this heterogeneity, it has to somehow be portable to run across multiple devices. But that's oxymoronic, because it's the opposite of what the ecosystem is trying to do, which you're shading for efficiencies. And you also have to worry about, like, the fact that these compute engines don't have much performance. Remember that, right? I can go on and on and on, but you hopefully get the general idea. Resource constraints, I already kind of gave you a little flavoring that, hey, like, the memory ends up being extremely tight. Now remember, the memory is also not only tight, it also varies quite dramatically from one platform to another platform, which means that even if I figure out how to deal with the ISA challenges, the instruction set architecture challenges, I'm gonna have to struggle with the fact that the memory capacities are radically different, which means I have to make very conservative sort of assumptions about how much memory I'm really gonna have. And of course, they don't really have too much power, right? That's another big problem. So which means, power is obviously key, because if you're an embedded developer, you're thinking about power most of the time, because it's your first and foremost thing, which drives into the resource constraints, which also drives into the heterogeneity aspects. That's just sampling on the hardware. There's much more I can get into if folks have questions. On the software side, it's also a hodgepodge mess, massive fragmentation. What do I mean? Simple things, for example, like, let's say you take your desktop environment. When was the last time, for instance, if you have written any code, right? When were you explicitly dealing with memory management? I mean, memory management is kind of thought as something like a textbook kind of a thing in the undergrad class, and then really you don't worry about it as much, because there's someone else who's handling it nicely wrapped around some sort of library feature. Now, typically when you're dealing with embedded systems, you don't tend to have nice portability and interoperability, because these libraries are going to be very specialized for a certain device. Why is it specialized? Well, because you end up chopping the ISA down. It has to be extremely customized for that particular domain. So which means that some of these devices will have libraries. Well, they have memory constraints, so some might not even have that library. So you can't even rely on a very simple thing like malloc, for instance. You can't even assume that, which is kind of bonkers. So you have to somehow understand, like, wow, not only is the hardware different, the software is also wickedly different. Operating system, I don't know. The operating systems, when you look at the real world for the big systems, what are you talking about? You're talking about something like Unix, Linux, and then Windows, pretty much. That pretty much kind of lumps it up, and there's a lot of portability between variations of Linux and so forth, right? Or Unix. So yes, there's differences in the big systems, but it's very, very limited. In fact, we have gotten very good about enabling interoperability in the large systems. Now, when you look at embedded systems, no, you can't assume that, because you don't have the compute. This is why I was talking about the compute. The clock frequency is low, which means whatever bit of compute you have, you can't be running fancy library code and operating system code in order to do management. It's going to really have to just be your application. So people often don't end up having operating systems. There are some embed OS and RTOS and things like that, but if you look at the ecosystem as a large, right, you don't end up having this. And when you're trying to build machine learning on top of these embedded systems, you cannot. It's a real problem to have the hardware heterogeneity, and it's a real problem to have the software heterogeneity, because you don't want to get into the business of, like, if I'm an engineer and I'm writing an inference engine, right, something that can take a neural network graph and then run it, right, knows how to interpret it or compile it in. I don't want to have to think about the fact there are, like, 50 variations of the chips. That makes it extremely challenging to be able to deploy a machine learning system. The reason TensorFlow, the reason PyTorch, and all these things work remarkably well, and the reason all of us are able to adopt them, is the fact that at the end of the day, if I take an executable, it's going to largely run no matter what system. It doesn't matter if AMD built it or Intel built it. It's an x86 ISA that's been nicely preserved, so it just runs, period, right? So that enables us to focus on this decoupling of this nice abstractions, versus in the embedded ecosystem, you have tight vertical integration, which actually makes it problematic when you step away from one chip or one vendor to another vendor. So this becomes a real problem, and you got to somehow figure out how to address this. So I'm going to get into the little bit of nitty-gritty weeds around how we can actually deploy machine learning, despite the fact that we have these challenges, if you can actually engineer a system intelligently. Now, one of the things I'm trying to do here is I'm going to name drop a couple of pieces of examples so that folks who are interested will know, okay, this kind of technology exists, so I can actually go check this out, right? So I'm going to do a little bit of name dropping and so forth, and try and make things a bit more practical, especially for students. So TensorFlow in a nutshell, right? So you can check out this paper that we wrote. It's a collaboration between Harvard and Google. It's out, and a lot of embedded system companies are adopting it. And I'll tell you why. So TensorFlow is something you probably heard about. It's a framework that allows you to train neural networks and able to do inferences. In other words, use this black box to be able to say whether it's a cat or a dog. Now, that's TensorFlow. Now, TensorFlow Lite is a variant. So there are 3 versions of TensorFlow in the big ecosystem. So there's TensorFlow, which is usually used for training or running graphs in data centers. There's TensorFlow Lite, which usually works on mobile systems because they're customized for Android and iOS and so forth, which don't have the same sort of memory assumptions you'd have in big systems. You also don't need to do training. TensorFlow Lite is all about just doing inference. You can't train a neural network with that code base. Then the third part is micro. Micro is something that we engineered, custom designed for microcontrollers to deal with all the crazy crap that I just kind of told you about earlier. So what it really has are some important characteristics that address some of the challenges I just talked about. First and foremost is that it's got a very small binary footprint. This binary footprint is important, remember, because you're talking about only having kilobytes of SRAM once you boot the system up. The core kernel itself is only about 2 kilobytes of memory. And if you run something like a keyword detector, like saying, okay, Google, and having the machine wake up, that'll take about 16 kilobytes, right? So it's still remarkably dinky in the grand scheme of things, and still leaves room for other things you might need to be able to do. It's got no dynamic memory allocation. In other words, you're not relying on any kind of library. Memory allocation is something that is controlled by compile time. Why is this important? Typically, this is extremely important in embedded systems, because when you talk to folks who are deploying things in the field, what you will very quickly realize is that when you want to deploy things in the field, especially in embedded system world, they want to be 100% that the code, once it's deployed, is going to work out of the box, period. There's no possibility of fragmentation or the OS potentially crashing. developers absolutely hate that part when it comes to embedded systems in the field. So therefore, you don't want any dynamic memory allocation. Everything has to be statically known that there's enough memory and period, bam, then you go. Then no dependencies on any kind of complex libraries. Again, this goes back to the point that libraries might not be homogeneously supported across all of the platforms. So you don't want to have library dependencies. And the build that you make has to be completely standalone, right? So that way you can deal with the fact that they're heterogeneous systems and so forth. No operating system dependencies, again, because operating system support is also not guaranteed. Ultimately, it's designed to be portable across a wide range of different systems. That's the key takeaway that you're going to have. I'm going to talk a little bit about how we deal with it. I won't go real bonkers on it, but there's an important aha moment that I want to communicate. So TensorFlow like Micro, when we design it, it's kind of designed to have an interpreter design. Now, typically, when you're talking about any system, right, where you have to run some piece of code that you wrote, right, you can either interpret the code, which is like what Python does. For example, it takes every single line inside your code and interprets, okay, you're saying add, okay, then it'll go emulate the add and then come back and say, okay, here's your result. Or what you could do is you would naturally compile the code down. Just use like something like GCC or LLVM and compile the code down into the raw bits that runs only on that one particular machine, which is usually okay in the big world because you're dealing with the x86 ISA, right? So you don't really have to worry that much if you compile the code down unless you do some specializations for the particular microarchitecture. But trust me, in the real world, no one really goes through that level of specialization in the code. What the system basically does is that, you know, it's got, there's a data part, which is effectively the model, right? So the data is actually the neural network, and then you have the instructions for like what the ops need to be. What op? I need to do a convolution. Okay, I need to do a max pool. I need to do something else. Right, so that's what the neural network graph is going to say, right? So what the dispatch loop basically does is that it actually, you know, it's looking at some sort of instructions that are coming in, and then it basically has some implementations, the runtime ops, or what it actually implements, right? Which is the actual backend that's kind of tied to this device. Or you can just run some sort of vanilla code that you've compiled it down to. Right? And just to again contrast this obviously looks like a lot of dispatch. You're going to have to look up what is the network graph looking like. Okay, I need to go do a convolution. Okay, then I'm going to go do the convolution. Okay, now it says the convolution, you know, is running on this matrix. So you have to do a lot of interpretation, which is usually really slow. That is known. This is why if you look at the performance of Python code, you would not use Python code in any kind of real-time system. You would often use compiled code, right? So compiled code is generally really fast, and more importantly, you actually end up doing very aggressive optimizations because you're compiling the whole binary down. What you can do is you can fuse operators inside the neural network into one, you know, small block rather than individually doing it. Versus if you look at an interpreter, if I have a graph that has got multiple stages, I have to systematically go one by one. A lot of the machine learning compilers will actually collapse certain nodes completely into a single unified optimization through kernel fusion and so forth. So the high level story here is that typically, you don't want to use interpreters. Interpreters are really slow. The nice thing about interpreters, though, is that they are usually platform agnostic, which is what's really interesting about using an interpreter design for an embedded system. But here's the problem. Interpreters are slow. Well, I just told you embedded systems, you know, are very concerned about the energy. So ideally, you want to be able to run things real fast and shut the system down. You don't want to be doing compute. Well, there's something interesting about machine learning that's inherently different that makes it super exciting to actually use the opposite. In other words, use interpreters because they actually give you that portability, because machine learning does something weird with its instructions. Typically, when you look at Python, for instance, you have a lot of syntax. And when you're parsing that syntax down, what you have to do is you're interpreting each and every single one of those statements. And so the overhead of actually doing the parsing with the interpreter, the dispatch loop, as we call it, that actually ends up being very significant compared to, oh, you have a very simple statement that says, you know, for something, right? Like it has to interpret that or add these two values. That's very simple compared to all the junk that has to happen on the dispatch loop. So if you take virtual machines class or dynamic compilers class, these are all things that are taught in that. So they're usually not a big proponent. Like no one's a real champion of them. But what's really interesting about machine learning is that, like, when you look at the quote unquote instructions, right? These instructions the overhead of the amount of time you spend inside that block relative to the dispatching overhead of reading everything and then dispatching which instruction I should execute, that block of code, like for example, a convolution is an instruction, right? It just says do a convolution, this is the kernel, and on that input matrix that's coming in, it ends up spending so much time inside that single operation that the relative overhead of that whole interpreter looks extremely small and dinky, which makes it super interesting for interpreter-based design. And this is the fundamental observation we make. And if you look at the whole network graph, for example, as I'm showing you a toy example here, right? If I'm spending many, many cycles, then relative to the amount of dispatching I would have to do, which is I'd have to do an initial dispatch, then I have to do a convolution dispatch, and a ReLU dispatch, a max pool dispatch. These dispatches are insignificant compared to the amount of time each of these ops is really doing. Just to kind of put this into context, I'm showing you here two example applications. I'll talk about them much more later. Right. But the point is, if you look at their total compute time and you look at the interpreter overhead, it's really, really insignificant. And that's the key thing. You could argue 4.1% is insignificant, but you got to remember that 4.1% is allowing us to design an interpreter that runs on any kind of embedded device, which is wickedly awesome. Right. And this data comes from this particular embedded system. That's all. So point I'm making here is that, the interpreter design is really cool because you can change the model, for example, without having to recompile the code, which is extremely important. Typically, what you do in an embedded system when you want to do something is you compile the entire application down to the raw part, and then you ship it out. What this means is that imagine now I have to do an OTA or over-the-air update, right? So I've deployed this device somewhere in the field, right? Now I find that, oh crap, my network is actually performing poorly. So I do some, I'm a data scientist, so I'll come up with a new model and then I'll push it. I want to push a new one out, but I can't because I need to physically be tethered to that device in order to flash the device, right? So that becomes a real problem. So what you usually end up doing is you'd have to physically be at the device. And the whole point of TinyML is that these devices are everywhere and you've got massive scale. So the notion of having people individually go and change things, that just doesn't work. And a concrete example, I'll come back to the technical stuff here. A concrete example is like when you're deploying things in the field, for instance. Imagine, for instance, that you deploy a smart sensor that is monitoring for wildlife in the middle of some Amazon forest, right? The whole idea of having that particular use case is that you actually are not going to be sending someone in to flash things, or you're not going to be replacing the battery often. So somehow these devices have to get updated. Now, one of the ways you can do the updates, if you have the right design, like an interpreter-based design, is that you can actually update the model through LoRaWAN. You assume that you have some sort of basic communication where periodically, once a month, the device comes up and then communicates and shuts down. It's a calm device, so you're not burning power for communication. If you use an interpreter, you can actually push the model as sort of, as an updatable thing, because you don't have to recompile it. It's just raw data, right? So that's what's extremely important about it. Like, gives you this massive flexibility, not only to deal with the heterogeneity, but also being able to update the device. And the same operator code can run on multiple models, can be used across multiple different models. Embedded systems don't necessarily run a single model. I'm not going to get into multi-tenancy stuff. But the point is that you can reuse a lot of code if you do this design. Again, key point is interpreters allow you to get portability, and you can use that across a large number of systems. This has always been true about interpreters. It's just that interpreters happen to be awesome fit for embedded devices. And that's what TensorFlow Lite does, and that allows us to kind of write code once and then be able to update models and run things differently. So you deal with a lot of those challenges that I mentioned earlier very easily. Another thing that I want you to keep in mind is that often, I have definitely seen a lot of papers. I'm a big fan of actually getting stuff running in the field. What you will often see is that, people will come up with some kind of Mickey Mouse version of an inference engine and say, hey, check out my inference engine. This thing is super awesome. But what you often forget is it makes for a cool little research paper. But then the problem ends up happening is that you actually have to when you're training the model, there's an entire suite of optimizations and everything that are done before you land at the inference engine, right? Now, all of that, what you want is you want to be able to reuse all of that existing ecosystem. And this is where some of the interesting research projects come about. They stay as research papers for a good reason. It's because you don't have that legacy part, right? Now, one of the things that we did very carefully when engineering TensorFlow Lite Micro is that we wanted to make sure it stayed in line with the TensorFlow, which means all the optimizations that happen in TensorFlow down to the TensorFlow Lite, which I mentioned earlier, all come free of cost. And you then do custom optimizations for embedded systems at the micro level, right? So you can reuse the existing pipe, which makes it an extremely important thing to have. That's the lesson that I'm trying to communicate. You need to maintain compatibility with the old tool chains. Now, this is something people often overlook, and I think this ends up being a real problem. Okay, so all right, so I talked a lot about the generalization aspects. I'm going to talk a little bit about standardization. So one of the things is that when you have all these different embedded systems, what you want to be able to do is you want to understand how these systems compare. So let's say you're an end consumer, and what you want to do is, hey, I want to figure out which device I should pick. So often someone's going to come in and say, you should take my embedded system instead of theirs because I have a better performance. Well, how do you sort of know what performance really means? Trying to decipher is one system better than another system is remarkably complicated in the machine learning ecosystem. The reason is because it's a very complex machine learning stack, right? In the TinyML case, you have many different sensors that have many different applications. They have many different data sets on which people are working on. They have many different models. So you need to know which exact model people are using. What is the framework they use? What is the inference framework on which they're running? Because all of the performance characteristics that come out of this thing are going to be very dependent upon this sort of a vertical stack. So if someone comes and says, hey, I have a classification accuracy, or I have a performance of this much for this classification task, you need to ask bazillion questions. So this has actually been a real problem in machine learning at large, right? So this is not an embedded system thing, but the embedded system, as I mentioned, due to all the heterogeneity and so forth, just makes it yet another big challenge. So if someone comes up with a result, it's some cross product of all of these different things. So what you want to do is you want to be able to decipher that mess. How do you go about doing that? So, well, first and foremost, if you look at the use cases that we have in the TinyML context, right there, you've got to think about it from the sensor sort of a perspective. You have audio sensors, you have image sensors, you have telemetry kind of sensors, and all of them have many different use cases, and they use many different types of machine learning methods. Not everything is deep learning, as I've been talking about. There are actual ML-based methods that are also used. And there are lots of different data sets that are associated with all these tasks. So we want to, first and foremost, if you want to try and get the industry to kind of be able to speak the same language when they're doing performance analysis, you got to be able to say, okay, what use cases are common and useful? Now, to do this, one of the things that we as an industry kind of did was we actually worked with MLPerf. MLPerf is something that does machine learning systems benchmarking. Is something I actually helped build for inference systems. And what MLPerf does is that it's really a community-driven effort where a lot of different companies all come together with many different universities being active. And the key goal is basically to understand how do we assess systems, right? So it's almost a science. It's like trying to figure out how performance evaluation of machine learning systems needs to be done. At large, I want you to understand what MLPerf is, because I think this is one of those lasting takeaways you can have. MLPerf basically builds machine learning benchmarks. Now, benchmarks often need data sets, and they have to be public data sets because everybody's got to use them. And you have training benchmarks and you have inference benchmarks. And ultimately, the goal is that MLPerf as a community, as an industrial community, kind of comes together in order to identify what are the critical tasks that we all care about. What are the important scenarios that actually matter? For instance, inference is done differently on an embedded system versus an autonomous car. There's just different use cases, right? The way the machine learning system is actually deployed is actually different. A lot of people don't think about these things. It's different, even in data centers. The way the data center machine learning model runs is different in terms of the way it's used on a car versus a phone. To be specific, for example, a car has to do, when it does inference, it has to do inference on all the inputs that are coming in from multiple cameras. That's not what you do on a phone, right? On a phone, okay, maybe you have 3 cameras. So, but by and large, you're only interested in the latency on the phone, for instance, right? But versus on the car, you have to process all of that within some sort of real-time constraint. So they end up defining scenarios. And there are a set of rules around, if I want to run a piece of code, how, what are the things that I can change and I cannot change and so forth. And then ultimately there's some machine learning metrics that allow us to compare systems and then, collect and publish results. I'm not going to go too deep into, more nuances around this benchmarking organization. It's something you should check out. But I'm going to try and very quickly pivot into the TinyML side of the world. But the ultimate goal when we're building benchmarks, right, is sort of like these metrics that we want to have is that we want to be able to replicate performance numbers. So if you have some embedded TinyML sort of performance number, I have a different TinyML performance number, we need to be able to compare them and say, okay, which embedded system should I really buy, right? But to do that, you need to have representative workloads. As I showed you, there are many, many different workloads, so somehow we have to subset all of that down. And ultimately, the goal is to encourage innovation, right? So you want to pick workloads that will move the field forward. And it has to be something fair and useful for everybody in the ecosystem, support both commercial entities as well as researchers like you and me, and make sure that all of this benchmarking is actually affordable. It's actually an important thing if you actually want to help everybody in the industry. Not everybody's going to have the same wealth and capabilities like Google, Amazon, Alibaba, and so forth. So it has to be something everybody can participate. So how do we go about building a benchmark in the system in order to do standardization? Benchmarks are critical for driving the industry forward. So there are a lot of different tasks. So you have to ask yourself some sort of big questions. A principled approach would be like, what is the definition of a benchmark, for instance, right? Machine learning tasks are often a mixture of machine learning, deep learning, and traditional non-machine learning code all put together. So what is the definition of a task? In our context, it's just going to be the machine learning kernel to keep it simple. In the selections case, like which task, like this is why I'm showing you this audio, this audio, video, telemetry, like how do you pick from all of those different use cases? Because you can't benchmark all of them. What is the proper definition of performance in an embedded system? And then, because of the heterogeneity that I showed you earlier on, when people are running machine learning models on their embedded devices, they're all going to be specialized and they're going to be different for different hardware. So you need to make sure like people are running the exact same code, right? So this is called mathematical equivalence inside machine learning models. It ends up getting really messy and complicated if you don't streamline this. And then of course, what kind of optimizations are allowed, right? So quantization, converting FP32 models into int8 is extremely key for some of the embedded systems. Even binary networks are actually being extremely important for embedded use cases. And doing things like calibration and retraining. What do you allow? What do you not allow? Bottom line, there's a lot of variability. It's a new application domain. So you have to streamline the process in there in order to make sense of the numbers. And then how do you show the results? Right. So I'm not going to slice and dice each of these, but hopefully it kind of gives you a question. And having that community there, kind of like, the community comes together to try and answer these hard questions. And that's what we did with TinyML, which very quickly I'll show you what those benchmarks are. So how do you pick a benchmark, right? So you don't always want to pick the latest and greatest kind of benchmark. For example, like you might run some sort of a NAS thing, neural architecture search and come up with some crazy network that no one's really heard about, but you claim like, hey, it's got this awesome accuracy. Do you pick something like that just literally came hot off the press on a research paper, or do you take something like a well-established and well-accepted in the industry, like something like MobileNet? So our general principle is to take something like that's cutting edge, but not absolute bleeding edge in the research community. You need a wide variety of different kinds of networks, right? So do we go everything with deep learning, or do we have a mixture of traditional machine learning like SVM, decision trees, random forest, and so forth? Well, most of the interesting, we asked this question, and ultimately most of the industry said like we're all going towards neural networks. It was kind of a surprising answer for me. And then complexity, like do you have large models that are like, say 600 kilobytes, or do you have also small models like things like 16 kilobytes, right? So you need to have a spread of different things because embedded systems are designed for very different use cases. Typically in traditional systems, in the big scale systems, you would often have machine learning systems that are capable of running a rich variety of different things. I might be able to run LSTMs, RNNs, transformers, convolutions, MLPs, pick your favorite kind of variant, right? I can usually run all these things. But when it comes to embedded machine learning, what ends up happening is that a lot of the vendors specialize, like I'm going to do just keyword spotting. I'm going to do just visual perception. Why? Again, because it goes back to the key point about energy efficiency. If you're trying to do too many things, you're going to blow up your energy costs, which you don't want to have. So you've got to pick a diverse range of these models in the space. And of course, ultimately, if you want to have a machine learning benchmark, no matter what crazy area you think, oh, predictive maintenance is really interesting. Okay, well, the key question that comes back is there a public data set? Very often you'll find that they're not great data sets in this space, but we got to start the ecosystem someplace. For example, in predictive maintenance, honestly, some of the state-of-the-art database data sets are really just synthetic data sets. They're actually not real data sets. They're collected from using toys where fans break down or those kinds of things. Of course, there's some other real data sets, but the industry hasn't quite converged in which are really representative data sets. So if you're interested in working in the space, you should really ask yourself the question is what's the ImageNet of TinyML? So ultimately, we got the industry together and we landed on keyword spotting, visual wake words, anomaly detection, and image classification. 4 tasks that we managed to rile up the entire industry to get behind for the first version. This might change over time. So let me talk about some of the details around this. Given that there's so much innovation at the heterogeneity level, right, across hardware and software algorithms and so forth, how do we define a benchmark to support all of these different use cases? You need to have some sort of principled approach, right? So the first thing is, what's the benchmark definition? Don't worry about what's in the middle. I'll kind of explain all of this as I go through. The key phases are really benchmark definition. A definition of a benchmark is what's the particular machine learning task we want. Keyword spotting, saying, okay, Google, hey Siri, and all these, you can imagine, right? These things are running at scale. Billions of these inferences are done across the planet on a daily basis. So it's a very, 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 very important application. And there's only one data set right now that's widely accepted, which is Google speech commands. In fact, it should be called Pete's speech commands. Now, Pete Warden, who's a very good colleague in front of mine, and in fact, the lead for TensorFlow Micro, he's the one actually kind of created this because he felt like there was no data sets. He wanted to kind of work in the space, but then he realized, well, shoot, I want to do machine learning in the space, but there's no public data set. There's only Google data set, which you can't publicly release, which has got awesome data, but you can't release it. So this has effectively become the speech commands, the data set for keyword spotting. And then there's this network called depth-wise separable convolution, which is widely accepted as having good accuracy, about 90% that you can achieve. So that's the model that we picked. Similarly, like that for image classification, I talked about person detection earlier. Is there a person or not in a room? That's called visual wake words, right? The idea is that you want to trigger some activity based on whether there's a person detected or maybe there's no person. So we use mobile nets, which is well established, and the visual wake words data set is actually an automatically created data set. I'll come back to this point later. It's actually really interesting. And then, of course, anomaly detection. One of the biggest use cases of TinyML is sort of seen in Industry 4.0 or smart manufacturing and so forth, where you actually want to have intelligent. You want to make the whole manufacturing plant really smart and intelligent. One of the active use cases of that would be predictive maintenance, where, for example, you would say that, hey, this particular belt machine or this particular fan or this motor is going to likely break because it doesn't have the same movement in the motion, right? So you can pick that from vibrations, you can pick that from sound. That's some anomaly, some input that's giving you an anomaly. And so one of the data sets that we use is toy Atmos. Like it says, it's a toy data set. In other words, it's anomaly data. It's a sound data set for malfunctioning industrial machine investigation and inspection, MIMI data set. From this, there's a particular variant called toy Atmos that's actually about whether some entity is going to break inside that. And autoencoders are really good at anomaly detection. And so that's the kind of network that we actually use. Right? And of course, basically, you could imagine something like a Ring doorbell or something that we have, where you do very limited classification of maybe 10 classes, right? So nothing surprising here. This ResNet is not a regular ResNet. It's just a ResNet 8. So all these models are effectively in the order of between around tens of kilobytes to, I think the biggest one is around 275 kilobytes. So fairly small models. So these are just the definitions of the models that the industry agrees on. Then how do you actually package it all up? Well, you have to build what we call as a reference implementation. A reference implementation kind of shows what pre-processing do you do, how do you time the whole execution of these workloads, right? So we chose a STMicroelectronics based platform, and we use the TensorFlow micro toolchain that I mentioned earlier for portability, and we provide models. Right? As you can see, this particular device has only around 640 kilobytes of RAM. That's on the upper end of an embedded system, right? but most of the models are actually smaller than half this SRAM size. Flash consumption is also only like about a megabyte. Okay, great. And then we actually work with industry, which is Embassy. Embassy is an embedded systems benchmark developer. So we brought Embassy, who does a lot of the sort of power and performance measurement in traditional embedded systems, together with MLPerf. And then we basically built this MLPerf Tiny benchmark, which, together, we have all this kind of code that allows us to benchmark systems out of the box. And we provide reference implementations, where the reference implementations are where we provide the training data, the training script, in order to be able to actually create the model. And then, that gives us model provenance. When someone comes and says, hey, I've got this network that's able to do this classification, you need to know what that original model source is, right? Because you need to be able to reproduce it. If you can't reproduce it, you can't say that that number is actually a faithful number. So we provide those kinds of things. And of course, you have a very complex stack that's below. So the idea is that we provide all of these things, and then folks who want to claim some sort of performance will take that and run that on the system. And we have two things called open division and closed division. Big idea here is closed division has a very strict set of rules. Open division says you just want to solve this classification task, do it however the hell you want to do it. Open division so gives a lot of flexibility. Closed division is like when someone says, I did this in the closed division, you know exactly what they did, right? And that's the beautiful thing about reproducibility at that point. But it can limit creativity, and therefore we have something called open division. All right, and then what are the metrics that we care about? Pretty simple, in fact. Like, most of the embedded systems, which you really, turns out, you just care about latency. Obviously, you care about accuracy. Often, I do want to double click on this accuracy point. There are a lot of benchmarks out there, not necessarily in the embedded ecosystem. At large, there are many different benchmarks that are out there. And what you will very quickly realize about a lot of these benchmarks is that people will claim all kinds of accuracy, like they'll report all kinds of latency numbers, but my gosh, you really got to look at that accuracy number. Even in academic papers, you'll find these nice little period, like design space sweeps. And I often write reviews and say, hey, you know what? Like, I don't need a 10% accuracy drop. Like that's just ridiculous. Like, no one cares about that regime of having a 10% drop, right? You might come up with some really good energy efficiency number, but I don't care because it would never be seen in production. Or like, there's really no value. Right. So, for example, like, if you're deploying like some sort of a health application, let's just say in a big system, imagine if you're a machine learning model that's trying to detect tumors in your scans, right, has 99% accuracy. Well, are you going to be happy if the doctor comes back and says, well, that model that we deployed at that point happened to have like 99% accuracy, so it kind of missed a couple of your tumors, so I didn't take them out, and so you're going to die in the next couple of months. That'd be awful, right? But that is literally the world that we live in, like those point percentages that, like, even a 0.3%, a 0.4%, I can tell you of production use cases that I've seen within Google, just a 0.3% drop, they'll be like, the developers will be like, well, that's a model I can't use, right? Because you got to think about the deploying scale and the implications of all of this. So you really have to be very careful around setting accuracy targets. I cannot emphasize this enough. Everybody understands where to look at accuracy, but they don't understand the importance of that actual number, how important that number is. So you've got to measure and make sure people meet that minimum accuracy, and then they show performance. And of course, energy is extremely key when we're talking about these kinds of systems. Just to kind of talk a little bit about some of the highlights that, when we built this in order to drive the industry forward, this is all in the section of standardization as to what, when I'm talking about things here. The whole reason you want standardization is because it allows the industry kind of accelerate momentum in a particular space. If you want TinyML to accelerate in the field, we wanted to kind of build this benchmark so that people can start competing in it and then be able to showcase various kinds of capabilities. So, for example, I just kind of cherry picked a couple of examples here. So, one of the academic institutions from China, designed a custom RISC-V MCU in order to be able to run these networks, which is kind of cool, right? Because it's microarchitecture design for these networks. And then, there's a software company that says, I don't really care about the software, but my job is really like, to come up with really cool and interesting optimization. So I don't really care about the hardware, but I can show you what my framework is capable of doing, right? So it's completely agnostic of the hardware, and they can show a range of different optimizations compared to the baseline TensorFlow-like micro models that we provide. Then Sentient, who designs, keyword spotting app, accelerator, does this remarkably well at like ultra low powers in the order of like just I think like 100 microwatts or something like that for running some of these deep neural networks. So it enables them to kind of show, hey, here's our capability. Now, this way is kind of nice because, for example, here, people were able to do things on FPGA and compare that. So it allows you to compare which one is more efficient and so forth, right? In this particular case, it was a bunch of academics from Columbia, UCSD, UCLA, I think, and a couple other places where they have a HLS for ML kind of tool chain, and they use that to actually automatically synthesize accelerators. And they showed, hey, like, look, we can actually handle industry scale workloads. There are a lot more details inside this paper. You can go check this out. But the key goal here was around like the whole notion of standardization, right? If you want to be able to move the industry forward, you've got to have a ruler that everybody is using the same ruler to compare their performance efficiencies and improvements, and that's extremely important. So, okay, so at this point, we've come through from talking about why ML is moving to endpoint devices. That's what TinyML is. Talked about some of the challenges we have in terms of resource constraints and so forth, and the heterogeneity. Then I talked about how do we deal with that heterogeneity through one implementation of TensorFlow Lite Micro. And then, I moved you through, okay, now we have the building block on a single system, but then how do you drive the entire ecosystem forward, right? How do you have competing organizations to kind of get together? So I talked about standardization through a benchmark, right? There might be many other ways to kind of move the needle forward as well. Now I'm going to talk a little bit about around accelerating. How do you get consumers of all this technology to be able to do something really cool with this technology? Now, when it comes to that, often you'll see like this is a classic machine learning workflow. You start from collecting your data down to deploying inference on the endpoint devices. Now, this is really cool. A lot of people will go real bonkers on this part, which is around like, let me come up with a cute little model and write my research paper, or, do something around this space. But I'll tell you, model-centric ML is really sort of like, that is like the 90s era at this point. I guarantee this. In the next 10 years, everything we're going to see is going to be sitting around the data. Because printing out models is going to be, yes, we will continue to do it. Yes, it'll continue to be important, but that is really not the hard part because we've built enough of the tools right now that the train has basically left the station. It's going to happen. Like we know how to do that stuff. The real focus has really got to be around collecting data. How do you collect data? How do you, what's actually involved in collecting data? Today, when we talk about data sets in this kind of context, we have a completely misguided viewpoint. Like it's remarkable. Like even government agencies and funding agencies have this wrong, I argue. Why? Because when we talk about data, we often talk about data set, right? It's an instance. Like Google does not go index the world's data and come back and say, okay, I'm done. Now you can ask me questions over and over, but this data was something that we created when we first started Google back in when was it, like 2003-ish or something, when they first started off. That's not what they're really going to say, right? Instead, they have built a computing system that actually continuously keeps, sharding data across and gets it updated. And you can find that needle in a haystack in the order of a millisecond, which is a remarkable achievement. And that is really what we need for machine learning. We need to be able to build data sets on the fly when given a task, and not, oh, for example, Pete created this Google speech command, so that's the defective. No, because there are a lot of other reasons you get in trouble. So I'm going to talk a lot about around this example that I've been using earlier on, which is around Hey Siri, or like, this notion of keyword spotting, right? Pick your favorite keyword. One of the biggest problems that I see in this space specifically is the fact that like when we talk about data sets, it's all around data for data in like very handful of small languages, right? One of my passions is sort of like, how do we enable TinyML applications specifically, but across localized or regional languages as well? Not everything needs to be in English. But there's a fundamental problem here. The problem is, you need data to train machine learning models. That is a requirement. Okay. Now, if you know that, one of the problems is how many data sets do we have? How many Google speech commands do we have for the rich set of languages that I'm showing you down here with with millions of speakers out there on the planet, right? You find that as you try and get more and more data, as you try and care for more and more people who speak all these rich languages, Mandarin, Hindi, Tamil, Chromo and whatnot, right? You find that the data sets availability just disappears. Many of these languages across the planet don't even have data. So which means you can't even start to train a model. So if you want to do this, everyone's going to have to go and build their own little data set. That is costly because there are many challenges in building data sets. First and foremost, if you want to build a data set, you got to understand a lot about data engineering principles. And that requires you to understand things from like, what's the problem definition that you're trying to solve? What exact kind of problem are you trying to solve? What, for example, if I want to do keyword spotting, okay, sounds good. Like, where is this device going to be deployed? Is it going to be deployed in a very quiet room, or is it actually going to be deployed in a very active and loud room? That's a problem definition. Seems very simple, but you got to get that right, because if you don't get that right, you're going to collect the wrong data, which means your model then won't be working in production. So problem definition is extremely critical. A lot of people underestimate it in creating data sets. And you got to have the right permissions and rights. Often people don't realize that, like, you have, like, just because you have a data sets, especially academic data set. I'm an academic, so that's why I'm bashing on academia. I've done these kinds of things myself, where it's like we don't think about, do we have the right permissions and rights set up for, for commercial application or use of a data set? It's one thing to write a paper. It's another thing to take that technology and actually be able to move it into a product and actually be able to use it. A lot of data sets that we have don't have the right licensing for commercial use. So this is a real problem, right? And of course, you got to have a lot of the right formatting and so forth. Then you got to, let's say you get all that right, and you actually got to go and physically gather the data, right? Which means you got to get the right people to get. Now, trust me on this, when you're gathering data, if you want people to kind of speak into it, you got to get the right people to kind of understand what they're doing, right? Because they're, words are said in many different ways. So you can't, which means that, like, if I say hello, or like, if I say namaste, like in Hindi or something, like, that's going to sound very different from many different people, which means I need to have the right diversity in that data set. So how do I actually go about hiring the right people? That is a really hard problem. Then you got to collect the data, right? Then you got to label the data. Often when you do all of these things, what you end up finding is that there are actually a lot of problems with the data sets. Ultimately, when you get all that data, even if you manage to do all of this, you've then got to verify and refine all of this data, right? Because maybe someone does all that, but guess what? Their microphone busts out half the time. And if you have a label saying that, oh, that is actually a valid thing, your network is going to start training on that thing because it's dumb, right? So you're going to have that problem where you're going to end up, if you don't verify the data, your data is actually going to end up affecting the network, how the network behaves, right? Then you might also have to do some really interesting things like data augmentation in order to supplement the data, because usually you need big data. Right? And of course, then the populations evolve, so you got to deal with what we call as model drift, right? Concept drift, concept drift and data drift are things where the data characteristics change, or like the population where the consumers actually exist, that population is changing, which means then you got to deal with this. Okay, so normally what do we do? This is a very manual and tedious process. This is not to say this has not been done before. There's obviously many different places, right? Like Common Voice, there's a lot of public corpus data out there. For spoken speech, Coco, for detection, object detection that I mentioned, ImageNet for classification that I showed you earlier, Waymo with a lot of segmented images that this is the reason I showed you all these examples, so I was going to use all those words here. Same with Kitty. As you can see, these are pretty big volumes of data, but the truth is it's extremely costly and tedious. Again, you've got to worry about whether you can go and make a commercial applications. A lot of these data sets are gorgeous in terms of being able to do research, right? But production use cases are inherently different from academic or like public data sets that do research. Why? Because I don't know, like let's say hypothetically, let's say we're doing person detection because I want to deploy TinyML in a security camera application. Okay, what does that need? Well, if I ask you to write the requirements, you will say, okay, is there a person or not a person in that image? That's rule number one. Okay. That data set, we can take something like, ImageNet or Coco, and we can, subset it to find enough of a balanced data set that has people and not enough people, right? But that's not going to work in reality. Their commercial applications, I have literally firsthand seen and talked to consumers off, like they say, like, it doesn't work. Yeah, that's because you took an academic researchy kind of data set and tried to use that and train the model and try and deploy it. The deployment scenario ended up being that they were deploying it as a security camera at nighttime. I'm like, of course it's not going to work. All the images that you've been looking at have nice lighting. They needed to create an entire new corpus, right? And manually collecting all this data to be able to have whether there was a person or not a person in very dimly lit. Okay, they did that. And then guess what? It still didn't work. Oh, because the camera that they ended up collecting all the data was different from the actual camera that they're using in production for sensing the data, for sensing and doing inference. This goes back to the notion of your sensors. You got to understand that your data collection has to reflect the exact same deployment scenario in an embedded system. Many people botch this up. It's incredible. And so you have a lot of problems around this, right? So data engineering becomes extremely problematic. And if you get the data part wrong, everything else is just garbage. So this leads into the question. Again, I talked about a problem. What can we do? I'm going to paint one particular solution, okay? And this is going to be, again, in the context of, data collection and processing. How do you create the data set? And effectively, my ambition for all of us as a community is to actually build automatic data set pipelines. So why do I care about that? Well, TinyML for me is the potential, lots of industry applications and whatnot, but I often tend to deal with things that actually interface with people, it's like, and that's sort of just my personal bias towards research. There's something about technology interfacing with people just makes me very excited. So if you take a home, right, and you say like, okay, we all want to have smart homes. Today we talk, for example, to Alexa, but in the future, I think my daughter, who's now 6, by the time she's a teenager, she'll be like, why don't we like touch all those things back in the day? What's this touching business? Why can't we just like talk to machines? In the future, in 10 years from now, everything is going to be conversational AI, right? The notion of touch, I think, physically is going to disappear. And so you could imagine walking into like, your kitchen or like your appliance, and you might say, start washer, right? Or start grind cycle. That's all you're going to say. And then it's going to start. Or you're going to say start cold wash, right? You might then say like, okay, turn on the lights, turn off the lights, set the temperature to this, right? Turn the blinds down, or, I don't know, turn on or turn off your security camera. All of these applications. So why am I mentioning them? Because it's conversational AI and comes back to the fact that I believe that we're going to have use cases where it's about limited vocabulary. In other words, it's a limited set of keywords that you care about. If we can create data sets for these different applications, somehow automatically, we're going to unleash or unflood a whole new range of applications. What's really holding back is not the deployment of machine learning physically on device. I talked about a lot of those things earlier, and I feel like that's almost like enough of the engine has started that it's going to be a solved problem. What we have not been focusing on, which I keep kicking and screaming about, is like we got to produce the ImageNet kind of sources for commercial applications of TinyML. So how do we go about doing this? I'm going to give you one example. So one thing we've done is like, imagine you have like words you care about. Like I want to train a model, right? I want to have a consumer device that can detect, these 4 words, up, down, yes, and no, right? Now I can go and manually build that data set, as I mentioned earlier, or I can try and build something like quote unquote Google, the example I was giving you with Google earlier, where I'm saying that I want to be able to automatically be able to just kind of generate a data set, right? Like I want to express a problem. I don't want to have to go collect the data set. You can't democratize this technology if every mom and pop shop has to go and build data sets and do all of this work mechanical. It just doesn't work, right? So we need to start building these newer technologies where I just say, hey, I want to detect these keywords. That's the model I care about. The system should automatically then go out, search the web under the right licensing structures and safeguards in place with the right permissions and so forth, and say, hey, you know what? There's a lot of transcribed speech on YouTube, on Creative Commons, on Common Voice, and like there's so many different things, or like available videos, TikTok and all these kinds of things, right? Wherever you have the right licensing, you might find, hey, there's actually transcribed speech there, right? So I might find the word up in the sentence that says he gazed up the steep bank. There's lots of corpuses like that, right? So imagine there are all these files out there, and there are, right? And if it's down, and there's a sentence down here that says pencils down, time is over, right? Just an example. And really what you want to do is you want to build a system that automatically does what we call as force alignment, and then extracts the right keywords out of this massive database of different sources of data sources you have. And all of this has to happen pretty much like on the live kind of thing. And so the intent is like, you take all these sentences which have all this audio, and then effectively it is, searching for it. Just imagine like a Google search happening on this thing, and then out comes this large corpus that you need for your particular use case, for example. And then you train a model, right? This is why I'm saying a lot of the training stuff and all that, the pipes are all existent today. These are the kind of pipes that we don't have today. And this is what we need to build if we really want to enable this technology and get everybody to be able to come up with some interesting use case. This is just for keywords and speech context. Maybe there's another one for vision, for instance. So obviously I'm crazily passionate about this. So this is a paper that we had submitted in Europe's data set. So we'll hopefully find out on Monday whether it gets in or not. But the point is that this is our first corpus that we just released, which is for 50 different languages. Many languages have never had a keyword data set. So this actually touches and creates an entire ecosystem of languages, language support for keyword spotting. There's over 6,000 plus hours of speech actually inside keyword speech, and it's all automatically generated, which is awesome, right? So just to kind of show you a sampling, we go from English, German, French, all the way down to some really rare languages. And the key thing is that we just chose 50 as a grand challenge for us. We were like, can we do this, right? And you can see that the data sets are not equal in that English has a lot, some of the languages don't have a lot. In some cases, we only have like 11 keywords. You might be like, what kind of data set is that? That is a good question. But I will show you that even 11 is 3x the data set that you need. I'll come back to that point. You can do some wickedly awesome work with a handful of samples. So just to put things into context, compared to state of the art, you can see, like, I mentioned Google speech commands is what most of the industry across TinyML, when it comes to speech, actually uses this as sort of the bread and butter starting point, because it's public, it's got the right licenses and so forth, but it's only for English. And it's got, this is this updated version where Pete Warden actually created like 35 keywords, and it's about 27. It's a great data set. I'm not bashing on it. It's an awesome data set, but good work always builds on the shoulders of giants. So this work, which Pete is also an author of with us, where we built this pipeline, targets a massive corpus. That's the point. Again, it's not so much, I'm just trying to give you a point example. The more important thing that I want you to walk away with is not this paper or this particular corpus, but more so how we got to this extremely large data set. And that is the key thing that I want you to keep in mind. There are startups to be made into this. There are entire industries, I bet you, that are willing, that are bound to happen around this space. And again, going back to this example, if you have a large corpus of many, many different keywords, you can enable a lot of different applications. So also one cool thing that I want to, this will probably be the only place where I actually show you raw data from a paper, is how can we, again, in the notion of accelerating, what can we do from a modeling standpoint? I focused a lot on data. I said, I don't want to talk about models, but I do want to show you some sort of very interesting work we can do in the modeling space real quickly. So we have this data set, right? Now let's say, something like, okay, Google is what you want to train, right? And you want it to be a multilingual thing, right? In any language, basically. You don't want to custom generate models for every single language. That's just like a 90s style in my head way of thinking. I really believe that you got to be able to train things from language. It also has structure, just like images have certain structure in them, right? Language has even more so, has a much more structure. So we trained a model, right? Bottom line is that we trained a model and across 9 different languages with the tests, with the usual test train splits, we got a model that's 95% accurate, right? Okay, so this is basically a good model. But more interestingly, what I want to show you though, is this model that we trained can actually work on any language. Now, that is wickedly cool. Why? Because it actually works on 13 languages, for instance, that it's never seen before from a large training corpus perspective. Right. So if you remember that long tail that I was showing you, I said a lot of languages don't have a large corpus of data. In fact, in the data set that I just showed you, we only had 11 examples, like 11 keywords, right, available. But the point I'm trying to make here is that, then how is it this particular model, which I'm not telling you anything about yet, achieves very good, accuracy, true positive rates, right? On languages that it's never seen before. Well, this is because there's a structure in the language. So if you train an embedding model, which is the keyword here, the embedding model can use to be fine-tuned very easily. So for example, if I say namaste in Hindi, but I don't have a large Hindi data set, I just need 3 examples or 5 examples of someone standing there and literally just saying that, and the model will fine-tune the last penultimate layer. Just to be a bit more specific, generally what you do is with the languages you have, you can train this general embedding representation, which has got some sort of backbone with some sort of, head that we have in the front. We happen to choose these specific parameters, but it's not really that important. you can then create this general embedding representation, right? So this embedding representation learns certain key structures and similarities in words across languages. And you can then just give it 5 examples of, like, say, namaste, right? And you would be able to fine tune this extremely fast, right? So then it'll actually be able to detect a keyword in any language, which is like, literally you can play the radio and do this. I forgot to include an awesome example, but we're actually working with the United Nations on this to actually demo the detecting keywords in extremely low resource languages, like in Africa, where there are many different dialects, we don't have large data sets. So then how can you kind of come up with something in there? But we show that we use this technology where you can just give it 3 or 4 examples, and then you tune it into the radio channels. And what it allows us to do is then kind of build a map of, like, where people are being sick, because in some places within Africa and so forth, it's hard to get people out because the technology doesn't exist and so forth. It's not like we're in a developed country. So, but we still want to, identify where people are sick and get the right things out there. So to kind of shortcut things, they often have radio, sort of the primitive kind of technology, which is awesome. So you can tune into it and listen to the keywords like COVID and mask and so forth. And then you can build a geographic distribution of where are these words being heard, because that means like something's going on in that community. And then you can direct your efforts, your limited resources, very constructively. So we're doing something cool like that around this. Last but not least, just about to wrap up in the next 2 minutes. I talked about TinyML. I'm also here, and one of the big reasons I'm here is because I'm excited about helping students and other people learn about this. So I'm going to talk about widening access to applied machine learning. We all talk about digital divide, where technology should be something that is accessible to everybody. Given how pervasively ML is being deployed, I think it's extremely important that people understand what this technology is, right? Because again, these small little devices are dirt cheap, and the next, Bill Gates, the next Steve Jobs, and so forth are probably somewhere out there in this ecosystem. That if we can just get the technology to them, they're going to change the world. So one of the problems around this is sort of like, how do you educate people, right? So I was talking about this 10 million servers earlier, if you remember, and there are 4 billion smartphones. These are fairly pervasive, right? But if you kind of look at the MCUs that I was talking about, all this TinyML stuff, there are billions of these devices that are just dirt cheap and everywhere. But if you look at it from a pedagogical academic perspective, there aren't really that many courses. Educationally, like, in the context of embedded machine learning, there's really no courses out there, which is kind of crazy. So that's one of the reasons, one of the things that we had done was that we actually put together a course, and we worked collaboratively with Google to do this, because, you really want to, when you're talking about machine learning, it's one thing to just kind of talk about it from a textbook standpoint, but industry also brings a very practical sort of standpoint. And so we collaborated with them to kind of, put together a course online, which a lot of students can take for free. Harvard has been awesome because they allowed us to open source all the materials, so others, teachers and students actually take the course and then teach it in their own variant. And one of the key things that I personally learned from working with Google developers and so forth is that, like, you've got to really focus engineers on this end-to-end stack. Don't focus them only on training the models, because this is the problem that they're physically seeing in the real world. There's a lot of students come out with this knowledge and have no idea about how the rest of these systems, rest of these parts of the pipeline actually integrate. And this creates a lot of problem in production scenarios, even within Google. So, we created a bunch of courses that are, students can take for free, where they go from understanding fundamentals of machine learning to actually interesting applications of TinyML, like the keyword spotting and so forth, predictive maintenance. And finally, in the third course, they actually go on to developing these things by actually, Arduino was awesome because we worked with them to build this custom kit that I'm showing you. So and I'm mentioning this because I think a lot of the community is very interested in this space, and everybody wants to learn this, and the industry is also getting behind and enabling the sort of to bootstrap the next generation to pick up this technology. So this is like a custom kit that we put together, which at bulk, we can basically buy this for $30 at bulk scale, which is still very costly in some places. So I've been actually trying to get industry to sponsor some of these activities so that we can actually get this into some of the extremely hard to reach places where people don't have money to get this, and customs and so forth actually adds a lot of price. It's been taken quite widely. So it's just another resource if you actually want to go and learn this. One of the key things that I try and teach in this, again, I brought in domain experts into this because I'm not an ethical AI expert, but nonetheless, we had experts come in and talk about what does it mean to build responsible AI. The reason I talk about this specifically in this class is because as we deploy machine learning in embedded systems, I think we have to be very careful, because these things are going to be on our bodies. They're going to be continuously sensing. We're unlocking something that we don't really know what we're mucking around with. So we have to be very careful about this technology. That's at least my perception of things. And so we made sure, like, we actually had experts come in and we built materials specifically for understanding what it means for responsible AI in the context of TinyML. And we do this in the context of design, in the context of development, in the context of deployment. That's not what the whole course is about. It's a portion of the course. You can learn more about this stuff in this paper, because we wrote out the pedagogical sort of underpinnings of how we think about it, how you need to teach it, and how others can actually reach out. With that said, I'm a big fan of sort of democratizing tiny machine learning. I think we're on the cusp of something new. I think the great things that are going to come out of this are really going to be the things that students do, the next generation, not what people like me do, right? We build the technology, but I think the use cases and the stuff is going to come from students. And I talked about my specific take in the context of how do we solve some of the heterogeneity problems? How do we get the industry to kind of communicate so that they're all speaking the same language, so we can actually accelerate the advancement that's happening in this space? And specifically, I'm very passionate about getting us to focus more on building data sets, and doing this not by creating individual data sets, by actually creating pipelines for data sets, so that we actually have live living data sets that's similar to code, which continues to evolve. We have versions of data that continues to evolve, right? Just like we have GitHub, there should be a data hub or something. I don't know. That's a good idea. Yeah. So we need to, that will help accelerate the adoption of this technology. So with that said, I know I've done a lot of talking, and I'm impressed that there's still people hanging on here. So hopefully you've gotten some things out of this whole talk. So, and with that, I'll stop sharing my screen and turn it back to y'all.
Thanks, Vijay.
Thank you for having me.
From the audience. There's one in the chat, Vijay.
Yeah. Let's see. Can you also give some insights on biomedical data sets? How can we build a data set, or where can we get these data sets? Yeah, so for EEG stuff, I'm not an expert on the biomedical side. I'm actually trying to get into the space right now. So I don't have a very confident answer. Now, I know there are some EKG or EEG kind of data sets that are out there that are public. Whether they're actually commercially useful or not, I do not know. I know that one of the big problems in this space has really been that, like, getting the data from hospitals is a real problem. I only know of like one other person who's a machine learning engineer who gets access to it, but he was saying that, like, as a faculty, like, he only gets to do it for research, but he can't actually, release the data set. Yeah, they can train the model, they can talk about it from a research standpoint, but he can't get the data. So I do not have an answer, unfortunately, but there's certainly some you can search and you can do the model research on. This would also be a time, if folks want to ask me more technical stuff or something, I try not to go too deep into the technical weeds, because I really was like, oh, make sure it's educational, not research. So.
Yeah, we also have the Gather Town space where you can hang out after the session.
Cool.
We have a networking session. I don't know if you have time to be around, Vijay.
Yeah, I have some time. The kids are sleeping, so.
Yeah. Could they say again what?
My priority runs around whether the kid sleeps or not. So.
Oh yes, yeah. Same here.
So it's afternoon time, so she's sleeping.
Well, thank you. What's the thing behind you, by the way? That tablet with the mirror. Yes.
Oh, that's for this edX course that I'm telling you. So
okay.
The first 3 courses that I talked about are all done. The last course that I'm actually doing is MLOps. So how do you scale this into production? That's why I was kind of talking about some of the pet peeve.
What do you do with a tablet and the mirror? I don't understand the setup.
Oh, it's like it's the